Hello and welcome to the C++11 Beginner Tutorials by Gamer2Creator. I'm Chris. Well, it's time now to talk about move semantics. This is one of the first new language features in C++11 that we've talked about. It's not just another class or another function that does something in the STL, but an actual improvement to the language. And it has yet another context-sensitive operator using the ampersand, and it's two of them in a row. Now, basically, it's declaring an R value reference. I'm going to declare a function. That passes around a foo object. Now this is a unique pointer, and you have to know that unique pointers always point to a unique dynamically allocated object. So if we copy a unique pointer, then we would have two unique pointers pointing to the same object, which you shouldn't do, because then both of them will try to delete the same object and you'll have problems. You could do that with a shared pointer, because that's what a shared pointer does. It shares them. So we have our pointer to a foo. It's a unique pointer, so it should clean up after itself. Now I'm going to add this to the other constructor. Okay, so what I want to do is I want to pass this pointer to our foo fighter class, but because we're passing it by value and not by reference, we're going to get an error. Because a unique pointer is not copyable. And it's really hard to read that, but basically it says that the function, which is actually its constructor, its copy constructor, is deleted, which means it's not available. It's because you cannot copy any unique pointer, or you would have two pointers which are no longer unique. So how do we get around this? Well, we could pass by reference, and then this object is not copied. It's passed by reference, and then this object is actually referencing this object because it's a reference. But what if we wanted to pass it to this function? And depending on what this function does, maybe delete it there or pass it back out. Well, we would have to actually capture it by value. But this is where move semantics come in. As you can see, I just used std move. That turns this into an R value reference. Now, I believe that this will actually work. We'll find out. This needs to return. And I'm going to return a null pointer for now. Okay. So as you can see, we are all the way down to here right now. This is the line that the program is on. It's within that function. And we've already created and destructed our object. Now, to understand what has happened, we created it here and gave it the value of this address. But then we moved it into this object here. So this object became the owner of this, and this is now empty. And I'm going to prove it to you in the debugger. So we're here, and you can see the pointer has a valid value. 800 and 600 is its fields. And when we step into here, step out, step into, and we get up into here, we can see that this pointer has that old value that was in this one. But if we come back to this function in the debugger and we look at this, you can see it doesn't point at anything. It's empty. This thing has taken ownership of it. And when this thing falls out of scope, it will be deleted unless we move it again. Okay. So let's say, yeah, we're going to move it yet again. We're going to move it back to the return value. And if this isn't confusing enough, we're going to stuff it back into the original object it came from. And you'll see that we're passing this object's ownership from object to object. And it'll still be destructed properly. So let's try this again. So we're here. We have our address. Just remember 849A. Step into, step out, step into, step over. Now this object has our address, 849A. Now we're going to move it again as a temporary return value that replaces all of that. We're going to step over, step over. Now we're back to here, step over. And you can see that foo_main has, once again, that address. So we've copied it around and moved it from object to object, and we never lost track of it. If we hadn't moved it here, it would have been destructed at the end of this object, or at the end of this function. Now, one thing that we did that we can improve on is actually make this an R-value reference. Okay, so instead of a reference, it's an R-value reference. And like I said earlier, here's the ampersand sign again, and it has yet another context-sensitive meaning. In this case, just like reference has its context between the type and the variable, it has the same context, but with two of them it means an R-value reference. Now there's an interesting thing about this, is that while it accepts R-value references, once you get here and it has a name, it's really no longer an R-value reference. You actually have to move it again. So you have to call move on it. And this is really just a cast to an R-value reference. So this is going to work pretty much exactly the same, only I believe this is going to prevent a copy. It's actually going to be passed by reference as an R-value reference. And then when we move it here, it's going to be stuffed into this. So it's going to go directly from here, passed by reference, and the next time it's moved into a new unique pointer is the return value, and then it's assigned back to where it came from. So we've skipped a move, basically. And as you can see, it was still destructed. I know that flashed quickly, but it was. Okay, now here is where you get into the real meat of why R-value references matter and move semantics. Yeah, I'll just make int pointer p int array int array. It's really about moving objects around and preventing unnecessary copies. In here we have a pointer to an array. We're going to fill that pointer with the address of an array, and we're also going to store the size. Let's see. And I'm doing this off the cuff here, so please bear with me. And I don't know why that got erased. Now what? There we go. And then we're going to initialize for int I. Okay, so in this constructor we've taken in two ints. One is the initial value for each object in the array, and the other one is how many we want in our array. We create our array, we store the pointer in a field here, and we create that array in the constructor. We also store the array size so we can loop over it and index into it without worrying about our bounds. So this should work well just as a regular class for holding a dynamically allocated array. We need a destructor. We'll say delete array mp int array p int array equals pointer. Alright. So here we know that as long as this class is constructed and destructed, we will always clean up after itself. This is called resource acquisition in initialization, RAII. It's one of those big buzzwords with C++11. Now, what that means is that you acquire your resources, such as dynamic memory, in the constructor, and you free it in the destructor. And this keeps all of your memory managed. So you're managing your memory properly by constructing it with and getting your data, and then you destruct it by removing your data. And every object you create and destruct has the guaranteed ability to call its own destructor. And we can prove this. I'm going to create a subscope. I'm going to call foo. I'm going to pass it initial value of and the size of 10. Okay, so I've got the constructor and the destructor now print to the console that they have been called. So within the scope, we're going to get right here. I'm going to step over it. You're going to see the constructor was called. And because this is the scope, it's now going to be immediately deleted. And the destructor has been called automatically for us, and the data was freed. Now let's do this one more time, and we're going to make sure that we have our data in here. The array size. And you can see at least the first object had the correct value. Because this is just a naked pointer, Visual Studio doesn't know how far to look inside that pointer starting at that address. So it just shows you the first one of that type, which is int. But we do see that the size is correct, so we're good. Alright, so we know that we've been constructing and destructing properly. We haven't used smart pointers yet, but we will. I want to show you how the naked pointer works first. Okay, so let's say though that we have a foo, but we have like 1,000 ints. We have 1,000 ints starting at this address inside of our foo. That's a lot of ints. That's 32,000 bytes. Or bits. Yeah, 32,000 bits. Anyway, that would be a lot to copy around all the time. So instead of copying, which we would have to write a copy constructor, and we'll do that now. I always use the name other. And then we say array size equals other dot array size. We have to initialize our np int array to new, because we're copying, so we have to copy the array as well. Int other.array size. So we've created our new buffer here because we're copying this object now. This is a copy constructor. We've created our new array and we've initialized it to the array size of the other object. And we've copied the array size into our new object here. Now we have to go through and int I equals 0, I is less than m. So unless I've done something really stupid, which happens, I can now make another foo2, and pass it the original foo, and it should copy this. So we'll have two separate arrays now within each foo. But because each foo owns that pointer and will destruct it within its destructor, our memory management techniques should be working. Okay. So remember 69A2 and 1000. As you can see, this hasn't even been initialized yet. There's nothing in here. It has an invalid memory address. So we step over. 69A2 is not this address. This is 69B2. So it actually has for its array a completely separate address, and yet it has the same value at that address for the first int. So we've essentially just copied the size and the array and the contents of that array right here in this copy constructor. Now, that's good, and it's useful sometimes. You really do want to copy an array, and you want to copy a object's data. But sometimes you don't. Sometimes you want to actually move the contents of what this object owns into an entirely new object. So what if we did this? What would happen? Well, first of all, we don't have a move constructor, which is what you would need here because we're calling a constructor. We're trying to construct this object, so we need a constructor. Before we were using the copy constructor. Now we want to move its contents. So let's see what happens if we do this. We've actually called the copy constructor. Now remember this, because we're going to copy the object here. But we don't want to do that anymore. Suddenly we've changed our mind. We actually want to move the contents over, which is a huge optimization, which couldn't be done in regular C++. You could not do a move, at least not in this way. So we're going to write a move constructor. Now here is the syntax for a move constructor. It's 2 ampersands, just like a reference, but 2 of them, and it's not constant because we are going to change this object. So we have mp_int array Okay, so that wasn't that hard in terms of code. It's rather similar to this, only what we've done is we've simply stolen this field and this field. We copied that pointer into our new object. We copied the size of the array at that memory location into the new object, and then we nulled out the old object. So this object no longer has any idea where that array is. It's null. And we told it its size is 0. This is what's known as an empty but valid state. There's no error here. It's okay to have an empty array with a size of 0. That's okay. So we've effectively taken ownership of this pointer that was in the other object, but is now in this object. We've moved it. And when this object that we moved into is destructed, it will now delete the object that we took. So this, instead of calling the copy constructor now, will automatically, because we made it an R value reference with move, it will automatically call our move constructor. And all we had to do was provide that move constructor. And as you can see, we immediately jumped into the move constructor. Now, other has 5fa2 as its MP array. When we step over, we've now moved that pointer into this object, taken the size as well, and nulled out the old one. And that, in a nutshell, is move semantics. It's really that simple. It's just a different constructor that steals values away. And it really is only useful if you have a pointer to data, because you just copy the pointer over and null the old one, and you've effectively stolen all of that data. And this is how unique pointer passes its data around. Unique pointer has a pointer to your data somewhere on the heap. And whenever you move a unique pointer, it passes ownership through a R-value reference into the new unique pointer, which now has ownership of it. And if that one falls out of scope before you move it again, it will destruct the object. Now think about this in terms of the STL. Think of all of the objects that use pointers internally to data. String, std string, has a pointer to a C string in it, and that pointer can be moved to a new string. Think how many times you've tried to copy strings to other functions or to other objects and pass them around when you could have been moving them around instead of copying that entire string of characters every single time, or passing it by reference. That was the old way. So it's a very important and very good improvement to the language. Also think of std vector. That's simply a wrapper around a dynamically allocated array. And what if you have a vector of some large object and many of them in your array? Do you want to have to copy those every single time you pass that vector around? Or wouldn't you want to just move that pointer over to a new std vector? That would be a huge performance boost, as well as you would have more control over when your objects are destructed or deleted, which is very nice. It's worth mentioning that there's one other aspect to move semantics, and that is the assignment operator. I mean, you can write any function that takes an R-value reference that you want, like I wrote one right here with Foo Fighter. But it's all about transfers of ownership and optimization. So really the constructor and the operator, the assignment operator, are the two big ones that you have to understand. And the assignment operator is like, if I were to assign an int to another int, you'd already have two ints. You'd have the first one, and you'd have the one that already existed, but you want to copy the first value into that one, or the first object into the second object. Not construct it, because it's already been constructed. That's the difference between the constructor and the assignment operator. So if we had two foos, and I wanted to say, alright, well I want foo 2 to equal, oops, new keyboard, equal the first foo. Like, alright, well I haven't wrote an assignment operator yet, as you can see, so it would use the default one, which will not work in our case. But we want to write an R-value reference operator equals foo other. So this is going to look almost exactly like our constructor, only we don't get to use this here. We have to do it all here. And we simply say np int array equals other dot np int array. So we're stealing the pointer. Now we're stealing the size. And now we're going to null out the old one. Yeah, the dot. And there we go. this is your assignment operator that is move capable, as it takes in the R value reference. So I'm going to go here, I'm going to run the debugger, and as you can see we've created two objects. I'm going to step into this, and what did I do? I stepped over, I think. I'm going to try that again. Stepping right over it. Oh, I made a little mistake. This has to be, for this to truly be an assignment operator, the reference. It has to return a foo reference. So let's try this again. We're going to stop right here. We're going to step into, now what? Oh, okay. So what I forgot to do here was actually turn this into an R value reference. And now it's going to call the code that I wrote we have to return here. There we go. We jump up here. So now we're actually finally within the move assignment operator. As you can see, the other is the old object, and we're going to steal its values. Stepping over, stepping over, stepping over, and nulling out the old ones. So its values are 0, and the new object, or the object that already existed but is being assigned, has moved and taken ownership of the old object data. And we had to return a reference to itself. Okay, so what was holding on, what was holding us up in the original part when we had this was that it was calling a function I didn't even write. It was calling the default assignment operator. And that's why it wasn't going into it, was because it was generated by the compiler for us. And it looks like this. So I'm not going to put any code in here, but I do want to show you that that will actually be called. And I keep forgetting to return. And there you go. As you can see, it chose the assignment operator and not the move assignment operator, because we didn't have an R value reference here. We just had a regular object. But now that we have the copy, well, the assignment operator that is not the move assignment operator, and we also have the move assignment operator, we can see that it will automatically select the right one depending on whether we have this as an R value reference or not. So that's how you tell the language whether you want to actually move this object or you want to copy it, by whether it's an R value reference or not. And we step into this, it jumps into the correct one with our R value reference instead of this one. Okay, I know this was a long video. Thanks for sticking around, and I hope you learned a lot. We're going to start moving into actually doing some real stuff. So I hope you'll stick around, and I'll see you next time.